Okay, so let me just start off with a warm-up question. Question is, you have two vectors, u and v. What is u minus v? Okay. What is u minus v? Okay, so draw me a picture. Draw a picture of u minus v. Turn to somebody next to you and just compare what you got. You can talk to these two. Okay. Who would like to say what it is? Where is it here? Float, go ahead.
You can just switch the direction of the arrow on V, so
Okay.
then the vectors are tail to tail. And so the vector goes from, or tail to head, they're in the right direction.
Okay.
And then it goes from the beginning, the initial of V to the terminal of U.
Okay. So it's this thing here. Right, so what Flo is saying is that, well, look, this is u, right, and this is v. V is going this way. If I think about negative v will just be the same thing, but going in the opposite direction. Right? Negative v is here, so if I take u plus negative v, well, that's going to be, if I take negative v plus u, that's going to be this vector. Right? So this is negative v plus u, aka v plus negative v. Right? Another way of thinking about it, maybe more primitive. You say, okay, this is v. Here is negative v. Right? I'm going to add that thing. Here's negative v. I'm going to add that thing onto u. It's very primitive. Okay. And then you get this thing. Right? So this is, so here's negative v. This is u plus negative v. This guy here is u plus negative v. And you can move back. Same thing. Right? This is v. This is negative v. I take the u. And I add on negative v. Right? I get u plus negative v, which is this side, which is, since these things are translation, don't depend on translation, you just slide it over there. Right? This makes sense, right? Because this u plus v is the thing you add to v to get to u, right? So we're going to add this on. It's that which you add on to v to get v. Okay. Okay. So now let's get started. Okay. So 13.3 dot product. So earlier we remarked that there is no good way to multiply vectors. Right? We defined vector addition, we defined scalar multiplication, but we didn't define a way of multiplying them. And so here is one way of multiplying vectors. It's called the dot product. So definition dot product. Okay. And let's suppose that we're in R3. So in R3, you could do it in R2, R4, Rn, however many dimensions you want. So suppose you have u1 vector, u1, u2, u3. we have v, another vector, v1, v2, v3. Okay. Then we define the dot product. The dot product u dot v is defined as, well, what is it? Who knows?
u1, v1, comma u2, v2, comma u3, v3.
u1, v1, comma, u2, v2, comma, u3, v3.
Yeah.
So is a vector. So when you take a dot product, you get a vector. You're a little bit off. It's close, but you're a little bit off.
You add them.
You add them. You actually add these things. It's not, one doesn't get a vector. So yeah, this is actually really helpful. You sort of like when you take a product of vectors, you get another vector. But the dot product actually is not such a thing. Rather, you take a product of vectors and you get a number. So that's sort of dissatisfying. So slightly dissatisfying. Right? Because you get a number, right? When you multiply two numbers, you get a number. But when you multiply these two vectors, you don't get a vector, you get a number. Okay, so it's not there's something slightly or maybe quite dissatisfying about this. Okay. So for example, right, if you take say 1, 7 dot -2, -3, right? You're just going to take the product of the corresponding components, right? So you take 1 times -2, and then you add on 7 times -3, so it's -20. 20. Right? So that's the dot product of these two vectors. Okay, so that's the dot product. Okay. Everyone okay so far? Nothing exciting. Right. Okay, so as before, we said before that our vector operations satisfy some rules. This also this multiplication. So as before, this multiplication satisfies some laws. Okay. First off, u dot v is equal to, well, what do you think?
V dot u.
V dot u, right? V dot u, right? Multiplication is commutative. Commutativity is satisfied. Right, and why is that true? Why is that true? Let's think about it, right? On the left, we've got u dot v. What's u dot v? Well, that's going to be u1 v1 plus u2 v2 plus u3 v3. See? And on the right, what are you going to have?
v1 times u1.
Yeah, v1 u1 plus v2 u2 plus v3 u3, which are the same thing, right? And then, so the point is that so this is going to be v1 u1 plus v2 u2 plus v3 u3. And the point is that because scalar multiplication commutes, then the vector dot product commutes, right? So it relies on the commutativity of the lower dimension to get this thing. So by commutativity of scalar multiplication, these are the same. Next, if I take u dot v plus w, what should I get? What's that going to count? Go ahead, Will.
U dot v plus u dot w.
U plus v, u dot v plus u dot w, right? As you expect, distributivity, we have a distributive law here. And do we have an associative law? Do we have anything like this? U dot v dot w equals u dot v dot w. Okay, it doesn't make sense. It doesn't make sense, right? Because, why not? Because here we're dotting these things and we get a number, right? And then we're saying is that you take a vector and you dot it against a number. So we have a number dotted against a vector. So that doesn't make sense, right? This dot, we're reserving for the dot product. So this actually is nonsense, okay? There is no associativity law because of the trouble that we don't get a vector out when we take the dot product. The closest thing we have is the following. If you take a constant, and this is sort of like the lame, very lame. If you take a constant and you scalar multiplication first, so you do scalar multiplication on the thing, you can slide the scalar multiple in, but that's not at all what you'd hope for associativity. This is more like commutativity. In any case, there is no associative rule for the dot product. Okay. Okay. Let me ask you a question. What is if I take a vector and I dot it against itself? What do I get? Right, so U is U1, U2, U3. Here's U1, U2, U3. You dot it against itself, and what do you get? I'm sorry, I forgot your name. Yes.
Yeah, Sarah.
Sarah. And what is your name?
Oh, my name is Brina.
Brina.
Brina. Oh, like Sabrina, except take off the S and the A.
Brina.
Yeah.
Oh, yes. But that would be a Brina.
Yeah.
Okay, the first S and the first name. Yes. Yes. Okay. Yeah, and what is your name, please?
No, I'm Paul.
Paul. I forgot.
Alana.
Alana. Okay, so yeah, what is U dot U? What is U dot U?
U1
Just tell me what it is. Yeah.
U1
U1
squared
squared plus
U2 squared
U squared
plus U2 squared.
U squared.
It's just the magnitude squared.
Right. Okay. So that is the connection I was hoping you would see. Right. This is the magnitude squared. Right. So there's a connection between magnitude and dot product. Right. The magnitude you can think of as the square root of the dot product of the vector against itself. So there's a sort of relation between geometry and dot product, right? At least between the dot product of a vector against itself. And in fact, there's a geometric interpretation of the dot product of a vector against another vector. In fact, the dot product of two vectors turns out to be the product of the magnitudes times the cosine of the angle between them. So where suppose you have two vectors u and v again, and you have some angle phi between them. The dot product, that number you get out actually has a geometric meaning. It says take the product of the magnitudes and multiply that by the cosine of the angle between them. Okay. Is anyone familiar with why this happens? Has anyone seen this movie? Does this look familiar to any of you? Something, you've got side lengths. You know, if you think of this in terms of triangles, well, you've got side lengths and then multiplied by the cosine. Yeah.
Law of cosine.
Law of cosines. Yeah. Yeah. So this is actually a consequence. So why does this happen? It's a consequence of the law of cosines. Yeah. So So the law of cosines, you may recall, says that if you have something like this, C, A, B, right, then so it says C squared. Law of cosines is some sort of superior version of the Pythagorean theorem. C squared is equal to A squared plus B squared, and then there's this factor that you throw in. Does anyone remember? 2AB times the cosine of the angle between. So this is like a Pythagorean theorem, right? But the difference is that it works on all triangles, not just right triangles. Right? For a right triangle, you see what happens. The cosine of the angle between is 0, right? And so this term vanishes, and you get the Pythagorean theorem back. Okay. So C squared equals A squared plus B squared minus 2AB cosine C. And now let's think what that says about if this is U, right? If this is U, and this is B, and this is U minus B, right? Remember what we had up at the beginning of class, right? If this is U, this is B, this is U minus B. Right? We've got this triangle, right? And what does this say? Here's the angle. So let's think about what the law of cosines says about our vectors. What does it say? Well, it says the length squared equals this squared plus this squared minus 2AB cosine phi. And somehow from the end of that, we're going to say that the dot product of U against V equals somehow this thing is going to imply that thing at the end. Okay. So from here to here. Okay. So take 2 minutes and see if you can get from here to here. Maybe 3 minutes. Yeah, feel free to talk to each other. Feel free to talk to each other.
Yeah, that's what I'm
Isolated me
Yeah.
but that doesn't mean anything to me. I'm trying to make dot products. I'm not
Just
sure.
play that
I'm sure it's easy.
Okay, so who would like to make a first move? What's a good first move? We want to get from here to here, right? We want to get from a statement which has a lot of magnitudes in it to a statement which has magnitudes and dot products in it. So anybody want to think about what would be a good first move?
Well, you can change the magnitude of u squared to the dot product of u times u.
Okay, great. So we could do that for everything if we wanted, right? All these magnitude squareds could be rephrased in terms of dot products. U minus v dot u minus v. This could be u dot u. This could be v dot v. This I'm just going to leave. I'm not going to change it to square roots. I'm just going to leave it because after all, I want this at the end. Okay, so right, we want the dot. This should be a statement about dot products. Well, let's bring in the dot product. That's a reasonable move to make. Okay. Okay. So let's look more promising. What should we do next? What can we do? What should we do? Yeah, Flo.
We can isolate magnitude of u, magnitude v, cosine of v.
Okay, so let's put that on the left side, the right side? Let's put it on the left side. 2 and I'll move this guy to the other side. So u dot u plus v dot v minus u minus v dot u minus v. Okay? You can divide that too. Okay. Now, what should we do? We're hoping that, you see what we're hoping for, right? We're hoping that this thing on the right, is u dot v. Right? Yeah, Peter.
By our laws, we can FOIL out there.
Exactly. Right. So we can do multiplication just like we do with numbers, right? So this is going to be minus u dot u minus 2. Well, there's going to be a minus u dot v and also a minus v dot u, and then there's a plus v dot v. So the point is that we can do everything just like we did back with numbers. Right? And you see what happens. Right? See what happens? The u dot u minus u dot u, the v dot v minus v dot v. And we have left over this thing, right? U minus u dot v and also v dot u, but those are the same, right? So we get minus 2 u dot v, we get minus 2, so we get 1/2 of 2 u dot v, which is c dot v. Okay. So you see, it's pretty straightforward. Right? From the law of cosines, you just put down the law of cosines. You say, what does that tell me about vectors? And then you bring in the connection between the magnitude and the dot product, and then you do multiplication and addition, just like with numbers. So pretty simple. Okay. Everyone all right? Anyone have questions? Anyone have questions? It's okay. Anyone have questions? Any questions? No? Some people are looking down. Okay, good. In any case, this is what you get. Geometric interpretation of the dot product, right? What did that number mean? It actually wasn't just some random number. It actually means the product of the magnitudes times the cosine of the angle between, okay, which is pretty useful, right? If we if we want, say, to find the angle between, right? So in particular, right, as a consequence, right, you can find the cosine of the angle between, right? If you have two vectors, and somebody says, what is the cosine, I'm sorry, what is the angle between them? Well, you can find the cosine of the angle, and then just take the arc cosine. Right? Take the inverse cosine, you find the angle. Right? So that's very convenient. Right? If you want, you've given two vectors, what's the angle between them? Now you can get it in a minute. Okay. What if the dot product is 0? What if the dot product is 0? And they're both non-zero, say. So you've got two non-zero vectors, and you take the dot product. What does that tell you? What if u dot b is 0? And these guys are non-zero vectors. Well then, don't blurt it out. Don't blurt it out. Don't blurt it out. Yes, yes. Give some indication. Go ahead, Melissa.
Well, I don't know, but are they exactly opposite then? Like pointing in
Let's
opposite
see.
directions,
So-
but they're parallel?
Let's think. So this would say that the cosine of the angle between them is 0. Right? The cosine is 0. If the cosine is 0, that means that the angle is 90 degrees. Right? So they'd be perpendicular. So u dot b, I'm sorry, u and b are actually going to be perpendicular to each other. And conversely, right, if they're perpendicular to each other, then their cosine's going to be 0. Then the dot product is 0. So this is pretty handy. You know, this is one very useful thing. You can figure out if when vectors are perpendicular to each other by seeing the dot product is 0. Okay. Another important application of this is the notion of orthogonal projections. Orthogonal projections. Orthogonal means perpendicular. If you don't like the word orthogonal. Okay. So here's the problem that we'd like to deal with. You have one vector, W, you have another vector, V, and you'd like to split V up. There's two ways of saying this. You'd like to split V up into a part that is perpendicular to W and a part that is perpendicular, that is parallel to W. So you'd like to split V up into this first guy, which is parallel, and the second guy, which is perpendicular, right? You'd like to express, you want to express V as something parallel to W and something perpendicular to W. Okay. Or the same problem, you just want to know what this guy is. Right? If we know one guy, we know the other guy. Okay. So we'd like to know if you drop a perpendicular from V onto W, what is this vector here? So this is V, this vector is W, and we'd like to know what this little guy is. Okay. And this thing is called the projection of V on W. Okay. So this thing, the projection of V on W. Okay. Well, and what we using what we just saw, we can figure this out. So you think, right, if this angle is theta, right? If this angle is theta, then V times the cosine of theta this is the, how should I say this? This is the sort of sine length of the projection. And I'm saying, I'm not, you might say, well, why don't you just say length, right? If v were going in the opposite direction, I would get a negative number, right? The cosine would be negative, and so I'm going to get a negative number. That's why I'm calling it the signed length. Okay. So, right. So what that is, the projection. Does that make sense? Everyone okay with that? Like cosine is going to be adjacent over hypotenuse, et cetera, et cetera. That is, the projection is going to be this sine length, right, times the direction, right? So that times the direction of w. Does that make sense? Right. You're going, right, you have W, right? And then let's say that this is, over here. Let's suppose that this is the unit circle here. So here's the unit circle. And then this little guy here is the direction of W. Right? This thing here is the direction of W. That's W over its norm. That guy is the direction of W, right? And we'd like to scale him out so that he's the right length, right? So we multiply that unit vector by magnitude of v times the cosine of theta, and that gives us the right length. Okay, so this thing is the projection. This thing is the projection. Right. So, but remember we can make this a little bit cleaner. Let's clean this up. Simplifying. What's the cosine? You recall what the cosine is, right? It's going to be. I'm sorry, the cosine in terms of the dot product and the magnitudes. So it's going to be one vector times the other vector over the product of the magnitudes. So this gives us a formula for the projection. So the projection of v onto w is going to be, v dot w over the magnitude of w times the direction of w. What we've written before was that it was going to be v times the cosine, right? Well, the cosine is the product, the dot product over the product of the magnitudes, right? So v times the cosine times, I should probably not use a dot since times the direction vector of w. So this v crosses out here, and you get v dot w over the magnitude of w times w over the direction, w over the magnitude of w. Okay. So this is, notice that this is a vector, this thing here is a scalar. Together, they call the orthogonal projection. The orthogonal projection of V on W. This thing by itself is called the scalar projection. The scalar projection. The scalar projection of V on W. So it's just that number. Okay, and then this is the number in the right direction. Okay, this thing is also called the component of V in the W direction. Okay, so this one it's a little bit involved, but this is how you answer that how you answer the question of, you know, if I had a vector and I projected I had a shadow onto the W vector. Well, what is that vector here? It turns out that, you know, trigonometry lets you figure out what it is, and then our knowledge of the dot product allows us to express it entirely in terms of dot products and magnitudes. So here's the thing that you want to keep in mind. Any questions? Let me do a very simple example. Okay. So let's do a very sort of dumb example. Let's say V is just x, y, z. Okay. And we project V onto 1, 0, 0. Okay. You already know the answer, but let's work it out. Okay. So let's take 1 minute and figure out what the projection of this thing is on 1, 0, 0. Okay, so first off, why is it completely obvious what the answer is? What's the answer, just from looking at it? You have some vector, x, y, z. You have some vector x, y, z, and you're going to project it onto 1, 0, 0. Right? What are you going to get?
It's just x.
It's going to, well, that's going to be the scalar projection. So it'll be x, 0, 0. It'll be x, 0, 0. Right, and if you project it onto 0, 1, 0, you would get 0, y, 0. If you project it onto 0, 0, 1, it would be 0, 0, z. Right? So it's sort of obvious, you know, geometrically that that's what's going to happen. And let's just make sure that it does. Right? So v dot i over the magnitude of I times I over the magnitude of I. Right? That's a projection. It is this, right? Well, v dot I is just going to be x. The magnitude of I is 1. The magnitude of I is 1, so we get x times I. in other words, x times the vector 1, 0, 0. In other words, x, 0, 0. Right? Which makes sense, right? If I have some vector and I'm projecting onto, onto the x-axis, I'm just going to get x, 0. Is this clear? Lily, is it okay? Yeah. Okay. So, and you can, we could do more complicated examples, but it's, I don't know if it's any more instructive we could, if you could just choose two random vectors and say, what's the projection of this vector on that vector, and then you work it out. So that's okay, so any questions? It's okay. Okay, so one last observation. That's one last related observation. So related observation. So let's go back and think. If you had on the unit vector, on the unit circle in R2. Let's go back to R2. Let's go back to the unit circle. Remember, if you have some angle theta, right, then this point has this point is cosine theta, sine theta. This thing is cosine theta, sine theta. Right? Okay. So now, what happens in R3? What about in R3? What about in R3? So so we have, say, we're on the unit sphere. We're on the unit sphere, and we have some point, some vector, u being x, y, z. So this is on the unit sphere. What you realize is this. This is, we can rewrite, let's rewrite this as u dot I, u dot j, u dot k, right? Where I, j, and k are 1, 0, 0, 0, 1, 0, etc. And then let's think about the geometric interpretation. So what's u dot I? Well, u dot I is going to be the magnitude of u times the magnitude of I times the cosine of the angle between, right? So this is the u dot I is of course the magnitude of u times the magnitude of I times the cosine of the angle between u and I. I didn't mean that. I didn't plan that. The angle between you and I. Okay, so this is the I vector here, right? And we have this angle between you and I. And then, right, so this is, so we get cosine of the angle between you and I, cosine of the angle between you and j, and cosine of the angle between you and k. So what does this say? This says that if you have a point on the sphere, right, if you have a point on the sphere, then its coordinates are actually cosines of these angles, right? Just like in the two-dimensional case, if you have a point on the sphere, then the coordinates here are the angles between are the cosine and sine of the angles from here of this angle, right? And similarly, in 3 dimensions, you get that this thing is the cosines of the angles between u and I, u and j, u and q, right? So this angle and this angle and this angle. So that's pretty cool. I hope you like it. I've never seen it used anywhere, but it's very cool. Yeah, and completely useless. Okay, let's stop there for today. Yeah, please turn in your homeworks if you